Hello everyone. My name is Mingzhao Huang and my partner is Yizhen Wang. Today we are going to talk about the high performance bimetallic copper bismuth alloy catalyst for the electrochemical reduction of CO2 to formate. This work is based on a two research paper focused on the MOF-derived and electrodeficit CuBi catalyst. First, we are going to mention about the background of the CO2 reduction reaction. As we all know, the increasing concentration of the carbon dioxide in the atmosphere is one of the most pressing environmental issues today. Converting the CO2 into a value-added chemical or fuels using renewable electricity offer a promising way to close the carbon cycle. One such product, Formate, is attractive due to its high hydrogen density and ease of transport. In this way, we can effectively control the greenhouse effect and alleviate the rapid consumption of the fossil fuels. However, achieving the selective and efficient electrochemical CO2 reduction to formate remains a major challenge. For example, the thermal catalysts require a high temperature and high pressure to activate CO2. Photocatalysis relies heavily use of sacrificial agents. The mainly problem is lack of high-performance catalysts. And here is the motivation that why we use bimetallic catalysts. The single metal catalysts like the bismuth, tin, or iridium have been explored for a CO2 to formate, but they often suffer from the poor conductivity or undesired hydrogen evolution. By combining two metals into a bimetallic catalyst, we can take advantage of synergistic effect. This includes electronic tuning, better stabilization of the intermediate, and suppression of unwanted side reaction. In particular, combining copper with bismuth has shown promise for improving the selectivity and overall catalytic performance. And the picture downward is the mechanism of the reaction pathway for CO and formate production from CO2. At the top, the pathway shows the CO2 being reduced to CO on the pure Vi or Cu surface. The reaction proceeds through the formation of the COH intermediate, which is reduced by the accepting electrons and protons to form the CO. At the bottom, the alternative pathway shows the CO2 being reduced to formate ions on the BiCu bimetallic interface. The reaction first forms a CO2 intermediate, which then goes through an OCHO intermediate, followed by the electron transfer to form the HCOO ions. Based on the reference paper, we synthesized the material via a one-step hydrothermal method, in which the reaction was carried out at 120 degrees Celsius for 10 hours. The precursor solution consists of an aqueous mixture of the copper nitrate trihydrate and the bismuth nitrate pentahydrate. The picture in the bottom of the page is a schematic the preparation process of the bimetallic CuBi catalyst. The rod-like CuBi MOF precursor were synthesized via a one-step hydrothermal method that we mentioned in the previous page. This precursor were then carbonized under argon at 600 degrees Celsius and oxidized in air at the 350 degrees Celsius. Finally, we can obtain the samples, and the sample proportion can be adjusted by the copper nitrate trihydrate and bismuth nitrate pentahydrate. And the picture is the SEM and TEM image that confirms that the MOF-derived CuBi-75 retained a rod-like structure with uniformly distributed nanoparticles. The CuBi-75 means the 75% of the copper, and the index mapping on the right-hand side shows the homogeneous distribution of the copper, bismuth, carbon, and oxide. The HRTM reveals the well-defined lattice fringe. This represents the atomic layers inside the crystal. Each fringe corresponds to a specific spacing between the planes of atoms. This fringe helps identify the crystal structure and confirm the crystallinity of the material. And the picture A is the XRD patterns. As the diffraction peak shows, the Cu100 and Bi100 are pure control. The CuBi75 and mixed CuBi75 both contain some mixed phases. The picture B is the Raman spectra. The CuBi75 and mixed CuBi75 shows the peaks from the both Bi2CO, CuO4 and other oxide, indicating the successful combination of copper and bismuth. The picture C is the XPS spectra of Bi. The CuBi75 shows a slight positive shift in the Bi ions binding energy compared to mixed CuBi75, suggesting a stronger interaction between the Bi and Cu in the alloy structure. The picture D is the XPS spectra of Cu. The CuBi75 contains both cuprous ions and the cupric ion state. The state-like peaks and relative intensity differences reflect the electronic interaction between the Bi and Cu, which can influence the catalytic performance. And this graph compares the XRD in different proportion of copper and bismuth. There is a Bi2CuO4 peaks around 28 degrees. For the electrochemical measurement, it's using the CHI performed in the 3-electrode system with 2 compartment cell. The cathode and the anode compartments were separated by the proton exchange membrane. It's the Nafion N117. It used the potassium bicarbonate as the electrolyte, the AgAgCl for a reference electrode, and PT nets at the counter electrode. And we drop the ink that mixed by the catalyst and naphthalene on the working electrode.
Now let's look at the electrochemical performance of most catalysts. In Figure A, we can see the LSB curves. Among all samples, CuBi75 show the highest current density across the whole range, especially at more negative potentials. This suggests that it has the most active surface for CO2RR. In Figure B, we see the Fe for Formate. Again, CuBi75 stand out with the highest Fe Formate value, reach up to 100% at minus 0.77 voltage. Compared to other samples like Cu100, Bi100, and even Bi2CuO4, CuBi75 consistently performs better across a wide potential range. In Figure C, the product distribution of CuBi75 shows excellent selectivity among security formats with negligible CO or H2 detected. Figure D confirms this long-term stability. After 20 hours of continued electricity at minus 0.77 voltage, the current density remains stable, and Fe format stay about 92 plus 4%, indicate excellent durability. To further understand why CuBi75 performs so well, let's look into connected and surface activity. In Figure A, the partial current density for Formate shows CuBi75 has the highest current density across a potential range. In Figure B, EIS data shows CuBi75 has the lowest charge transfer resistance, meaning that electrons can move more easily through the catalyst. Figure C shows a Tafel slope. CuBi75 has a slope of 101.05, which is lower than all the other catalysts. Lastly, in Figure D, we examine the ECSA. CuBi75 again outperforms others, confirms that it provides the most accessible active site for the CO2RR. Altogether, this result confirms that the MOF-derived CuBi75 catalyst achieves its excellent performance thanks to a combination of efficient charge transport, higher surface area, and favorable reaction kinetics, primarily enabled by the formation of a Bi2CuO4 interface structure. Then we read the other paper. In this study, the author present another approach for fabrication carbon bismuth bimetallic electrodes, but instead of using MOF, this directly deposit copper and bismuth onto thermally oxidized copper foam using an electrochemical co-deposition method. The key idea here is the separated growth of copper and bismuth atom, forming a tiny bound most like microstructure. This structure provides a high surface area and facilitate efficient CO2 mass transport without requiring any polymetric binder or conductive active like naphthalene or graphite. However, it's important to note that the focus of this paper isn't just on the material synthesis. The author mainly explore how different electrolytes and membranes influence the performance of CO2R. Let's look at this slide. In the EIS plot at the top left, we can clearly see that using KOH as the electrolyte leads to much lower charge transfer resistance than KHCO3, which means faster reaction connectivity and better electric conductivity. In the top right graph, we observe the long-term current density. The system with KOH and AEM maintain a stable current density of around 28, while the KHCO3 system with a CEM reach only about 16. Look at the bottom two graphs, which show FE under different conditions. On the left, with the AEM, the catalyst achieves a maximum performance FE of nearly 94%, higher than that obtained with the CEM shown on the right. In the CEM case, hydrogen become dominant, especially at more negative potential. The reason is that CEM allows hydrogen ion to migration from the anion to the cation, which promotes HER, reduce the selectivity toward formate. In contrast, the AEM block hydrogen ion crossover, suppressing HER, and helps maintain a high selectivity for formate production. So overall, this likely clearly demonstrates that the choice of electrolyte and membrane is just as important as the catalyte itself when designing an efficient CO2R system. To conclusion our presentation, we compare two catalysts with the same copper and bismuth ratio, copper and CuBi 50. As we can see from the chart, the MOF CuBi 50 shown on the left maintain formate Fe about 90% across a broad potential range from -0.6 to -1 voltage. Meanwhile, the electrode deposit CuBi 50 shown on the right only achieves over 90% Fe in a narrow range. This is important because potential close to zero voltage means lower energy consumption. Therefore, we can conclude that MOF CuBi 50 provide better performance, offering a wider and more energy efficient operation window for the selectivity formate production. So finally, here's the conclusion of our presentation. First, a new phase of Bi2CuO4 was successfully formed at the interface of the CuBi catalyst by the MOF framework. This phase has a crucial role in enhancing the catalytic behavior. Among all test composition, CuBi 75 showed the highest current density and higher formate selectivity and maintained a wide applied potential window. DFT conclusion further supported this, showing that the OCHO phaseway has the lowest free energy barrier, confirmed as the preferred route for the formate formation. As for system optimization, using AEM result in much higher formats efficiently than using a CEM. Lastly, switching the electrolyte from KHCO3 to KOH not only increase the total current density, but also reduce the solution resistance. This result highlights the importance of both catalyst design and electrolyte membranes configuration in developing higher performance system for CO2R to formate. Here's our reference. Thank you for your attention.